video. Okay. And we'll do that. Okay. Okay, let's see. Sorry. It's nice when it works every time. Oh yeah, that's started. That's this weekend.
Yeah. I've probably already watched about 6 hours of free coverage.
Really? Yeah, it's really good. Sorry, that's my notes or something else. Okay, so let's see. I need to go to 3,300. Let's do that. And there it is. Veterans Day, right? Okay, let me get through the name. Lopez. Look at how far.
Justin Michelle.
So, did you take a Friday or?
I took it on Wednesday.
Yeah. Right. That one socks on. Okay. Okay, can people hear me on Zoom?
Yes.
Yes, good. All right, so what we'll do today is we'll start off by reviewing. So last time we were talking about taking a linear transformation and expressing it in terms of various bases. So let me kind of give you a brief review. So recall we had T, and this is a linear transformation from V to V. So V and W are subspaces. You know, like Rn and Rn. And what we did was we took two bases. So beta, which was V1, V2, up to Vt, is a basis for V. And then we had a basis for W. So C was W1, let's say WR. And this is a basis for W. Okay, so what we can do is we can write the matrix T. So I'm going to say it this way. So if I take T on X relative to C, this is going to be C1 T on V1 of C, the coordinate, plus CR T on WR relative to C. Okay, and here our X here is written in terms of coordinates for V. Okay, and so another way to write this is that T of X on C is given by matrix times the coordinate X with respect to beta. And what matrix do we do? Well, we just look at the images on each of the basis vectors for V, and we take their coordinates and put them down the columns. So VT, C. And remember, this is the matrix M. All right, so to figure out the matrix M, what you do is you take a basis for V, you apply T to it, and then you write it in terms of the coordinates for the basis for W. Okay, and then just put things down the columns. Now, there's a very special case of this, and that's when V and W are the same. So special case is when V is equal to W, and we just take the same basis for the space. Okay. And then, so M here is going to be called T of beta. Okay. So again, I'll just write it out. You take the basis vectors and you write them in terms of beta everywhere. And you take the coordinates and you just put them down the columns. Okay, we did several examples of this last time. Are there any questions on this idea? Okay, now, why was this important? Well, it was important in terms of the idea of diagonalization. So it turns out that if I take a matrix which is diagonalizable, and if I think of it as a linear transformation, then if I take the basis of eigenvectors, then it turns out that the T of beta is just a diagonal matrix consisting of eigenvalues. So this is the theorem that we proved last time. So let A be an m by n matrix that is diagonalizable, okay? And beta be a basis for Rn consisting of the columns of P. Okay. Where we know that A is going to be equal to PD P inverse. Okay, so we saw that when you have A being similar to a diagonal matrix, then the P will consist of eigenvectors. Okay, so the P, matrix P, consists of eigenvectors for A. Okay. Now, if I have a linear transformation T of X, and it's just given by applying A times X, then if I take T relative to the eigenbasis, the matrix I get is just the diagonal matrix T. Okay. So A may not look like a diagonal matrix at all. I mean, T relative to the standard basis just is A itself. But relative to a different basis, namely the eigenbasis, or basis consisting of eigenvalues, then the linear transformation is represented by the matrix T instead. Okay, any questions on this? All right, so let's do some more examples to finish things off. Okay, so first of example is let T be a linear transformation from R3 to R3. Okay, and the basis, so beta, the basis, I'm just going to give it to you, is V1, V2, and V3. Okay, some basis for R3.
Yeah.
Okay. Now, I want to define the linear transformation by telling you where it sends a linear combination of the basis elements to. So if I take T on A0 V1, let me change that a little bit here, just so it matches up. Okay, so I'll make the subscripts kind of match up. That would be nicer. So let's call that A1 V1. Okay. A2 V2 plus A3 V3. Okay, so this is a linear combination which gives you a typical element in R3. And then I'm going to send this to 3A1 V1 plus 5 what? 5A1 minus 2A2 V2 plus 4, let's see, I guess it's A2 plus A3 V3. Okay, so this is how the linear transformation is defined. Okay, so the problem is find T with respect to this basis, this matrix. Okay, so let's kind of review what T of beta was. So in order to find T of beta, what do? Put it up here for your reference. So what should we be doing?
We have to write each of the vectors in terms of the basis.
Yeah, so you take the image of T1 and the image of T2, V of T2, and then you take T of V3, and you write it in terms of the coordinates. right? Okay, so let's do that. So what is T of V1? Well, if you look at the formula, that's basically when what A1 is 1. And so here I have A1 to be 1, A2 to be 0, and A3 to be 0. Right? So we just plug it in. Okay. So we get 3V1. Okay. The next one is 5V2. And the last one is 0V3. Okay. So everyone see how we did that? We just substituted in A1 to be 1, A2 to be 0, A3 to be 0 to get the value of T of V1. Okay. Let's do V2. So here A1 is 0, A2 is 0. Oh, sorry. Take that back. A2 is 1 and A3 is 0. Okay, so we substitute those values in and let's see what we get. So A1 is 0, so we don't have anything to do the first one. And then A1 is 0, A2 is 1, so I get -2 V2. And finally, I get 4V3. Okay, and then finally, T of V3, what do we get? So here A1 is 0, and A2 is 0, and A3 is 1. Okay, so we get 0, 0, and then V3. Okay. So what is the coordinate of T of V1 with respect to the basis? Anyone?
Coefficients down the columns. So 3, 5, 0.
Good. 3, 5, 0. So we'll write each one.
0, -2.
Okay, okay, hang on. Okay, so the next one is 0, -2, 4. Good. And then finally, T of V3 with respect to B, what is that? 0, 0, 1. Okay, so we have these things with respect to coordinates. And then finally, if I take T of beta, it has to be a 3 by 3 matrix. And I just put these vectors right down the columns. That's all I do. Okay, does everyone see how we did that? Okay. Okay, questions on this? All right, so here's another problem. All right, so let me see, I'm going to call this 2. So let T be a linear transformation from R2 to R2. And I'm going to define it as T of X is going to be the matrix 3, 4, -1, -1 times X. Okay, so it's A times X, where A is this 2 by 2 matrix. Okay, and the beta here is going to be, consists of the vectors 2, -1, and 1, 2. Okay, so if you want, this is V1, and this is the vector V2. All right. So what I want to do is I want to find T with respect to beta again. Okay. All right, so what should I do?
Find TV1 and TV2.
Good. All right, so first, find, well, what's TV1? That's going to be equal to 3, 4, minus 1, applied to 2, minus 1. Okay. All right, so let's see, what is that going to be? So that's going to be 2, right? It's going to be 6 minus 4. And then I have minus 2 plus 1, that's minus 1. Oh, looks like this is an eigenvector, okay? All right, and then I want to do TV2. Okay, so same deal, 3, 4, minus 1, and V2 is 1, 2, and I get out of this what? I get 3 plus 8, that's 11, and I get minus 1 minus 2, that's minus 3. Okay, 11 minus 3. All right, what do we need to do next?
Find the bases of each.
So we need to write 2 minus 1 as what? Yeah, so you have to find the coordinates, right? So in particular, you need to find TV1, and you have to express it as C1 times the first basis vector plus C2 times the second basis vector. Right? Okay. So in other words, let's just do a little substitution in here. 2 minus 1 has to be 2, 1, minus 1, 2 times C1, C2. Okay. So how do we find C1 and C2?
Gaussian elimination.
We can what?
You like put 2, -1 with the other matrix and then Gaussian elimination.
Right. So there are several ways we can do this. We can use either Gaussian elimination, or we can also find the inverse. Okay. So let's just find the inverse here. Okay, so let's call this matrix something. Let's call this matrix, I don't know, let's call it Z. Okay. So what is Z inverse? It's 1 over the determinant. That's going to be 5. Okay. A and D get switched, and you negate these two. Okay, so that's the inverse, 2 by 2 inverse. All right. And then you just bring it over to the other side. So then Z inverse times 2 minus 1 is going to be equal to C1, C2. Okay. And, you know, you could see what C1 and C2 have to be. So this implies that C1 and C2 have to be 1, 0. Right? I mean, it makes sense because, you know, you look at this equation, right? You have basically 2 minus 1 is equal to C1 times 2 minus 1 plus C2 times 1, 2. So you can set C1 to be 1 and C2 to be 0. And you know this, the solution is unique. So that gives it to you. Okay? So the coordinate here with respect to beta is going to be 1, 0 for T for V1. All right, so now what you do is you just do the same thing for T of V2. Okay, so repeat for the coordinate T of V2. right? And what you eventually get is 5, 1. So you get that the coordinate is 5, 1. Okay, so now finally, T of beta. Okay, so it's a 2 by 2 matrix. So what matrix do we get here?
1501.
Very good. Okay, so basically you put the T of V1 with respect to the basis beta down the first column, and then T of V2 with respect to beta down the second column. And that's how you get the matrix. Okay, so you should be able to do this anytime. You know, if I give you enough time, you should be able to actually crank this out. All right. Question, right?
So, 2, -1 is an eigenvector, correct?
Yes.
So if we had another eigenvector for E2, they're just the base, the coordinate for E would be just the identity.
Right. Well, it may be a scalar times the identity matrix.
Right?
Yeah. But see, that makes sense because, I mean, in some sense, if you have your basis consists of eigenvectors already, then your T is going to be a diagonal matrix.
Right, so you need to change it.
Well, you just have to figure out what eigenvalues you need.
Right.
Yeah. That's right. So it's really the what you're asking is sort of the former theorem we showed. Okay. Good. All right, so now what we're going to do is we're going to move on to complex eigenvalues. All right, so I have to kind of remind you what complex numbers are. So a lot of times what you want to do is you want to join the square root of -1. Okay, so this has got an imaginary number. And you know, if I square this, I get -1. So notice that I squared is equal to -1, and I squared plus 1 has to be 0. So really, I is a root of the polynomial x squared plus 1. Okay. So we know that whenever you have polynomials, like even quadratic polynomials, you know that the roots may not be real numbers. They could be complex numbers given by the quadratic formula. All right. So what is a complex number? Well, complex numbers are the form a plus b times I, where a and b are real. Okay. So a lot of times, if you take the complex numbers, which we sometimes refer to as C, then C can sort of be identified with R2. So if I have the point AB out here, this identifies with the complex number A plus BI. Okay, so in some sense, you can sort of put the complex numbers on the real plane. You know, oftentimes we do that. All right, now there's an operation called conjugation. Now, the reason why this is important is because when you think about the quadratic formula, then if a plus bi is a root, then a minus bi is a root too. Okay, so if I take a plus bi, and if I take its conjugate, this is A minus BI. Okay, so A minus BI is the conjugate of A plus BI. And you know, if you conjugate twice, you get back to where you started. Now, we can sort of do this in terms of tuples also. So if x is equal to x1, x2, up to xn, and these are all in all complex numbers, so they're tuples in the complex numbers, then if I sort of bar everything, then all I do is I take the conjugate on each of the components. And of course, this is still in the complex numbers, C to the. All right. Now, let me give you an example that we'll play off of. So I want to start with a 2x2 example. So A is going to be equal to 1 minus 2, 1 and 3. Okay, so this is a matrix with real coefficients. Okay, they're real numbers. Now, let's try to find the eigenvalues. So first of all, I want to find the eigenvalues of A. Okay. Well, how do we do that? What should we consider? Good. So we want to take the characteristic polynomial, which is the determinant of A minus lambda I. Okay, so what we do is we subtract off lambda from the diagonal and then take the determinant. So I have 1 minus lambda here, minus 2, 1, 3 minus lambda. Okay. And so we take a 2x2 determinant. So this is 1 minus lambda, 3 minus lambda, and then minus 2, and I take a negative sign, so it's plus 2. Okay. And we really want to just look at the roots of this. Okay, so let's simplify it a little bit here. So this is going to be equal to 3. Let's see, minus 3 minus 1, so it's minus 4 lambda plus lambda squared plus 2. So this is going to be lambda squared minus 4 lambda plus 5. Okay. So the question is, does this factor at all?
Yes.
This one looks like it actually factors. Did I make a mistake in terms of, let's see here. Let me just look at this for a second. C. Oh, that's weird. All right, let's write the quadratic formula out for a second. So minus b is what, 4? Plus or minus what? B squared, which is 16 minus 4. A is 1, C is what? 5. Over 2, right? Doesn't factor. Okay. All right, it doesn't factor. All right, so now let me just clean this up a little bit. 4 plus or minus. So it's 16 minus 20, that's minus 4, all over 2. And so now I want to find out what the roots are. So this is going to be 4 plus or minus, okay, this is going to be 2i over 2. So that's going to be equal to 2 plus or minus I. Okay, so those are the roots. Now eigenvalues. So lambda is equal to 2 plus I and 2 minus I are the eigenvalues for it. Okay, any questions on this so far? All right. So now let's look at what the eigenspaces are. All right, so we have the eigenvalues. So the next thing I want to do is I'm going to find the eigenspaces for A. Okay, so I'm going to take each eigenvalue and I'm going to find its eigenspace. So let's say I take lambda equals 2 plus I first. Okay, so I have to look at A minus lambda I. And so what matrix do I get here? Let's be a little bit careful. Okay, so I have to subtract off, this is 1 minus 2 plus I. I'll just write it in so we don't goof up anything. And then I have 3 minus 2 plus I. Okay, is everyone all right with this so far? All right. Okay, so what do we get? We get minus 1 minus I. I got minus 2 here. And I get a 1. And I get a 1 minus 1 minus I. Okay, I mean, make sure you don't confuse I's and 1s, okay? So I want to, maybe I should move that, maybe I should dot the I's a little bit more. Sort of bold. All right, so what do we need to do? We need to find the null space. So here we go. So minus 1 minus I, and minus 2, 1, 1 minus I, 0, 0. Okay, now, what I could try to do is I could sort of multiply by 1 over minus 1 minus I on the top, and then try to cancel that out. Or let me just multiply the second row by minus 1 minus I. That'll make things a little bit easier, okay? All right, so now we will perform Gaussian elimination carefully. Okay, so the first thing we get is 0. So we're gonna add those two together. And then what do we get for the second thing? Well, we have to multiply everything out, right? So if I take, let's just go over here. So if I take minus 1 minus I, 1 minus I, I'll just keep the minus sign outside. So I just have to multiply. So I got minus 1, and then I get minus I plus I, so the middle terms cancel out, and then I get minus I squared. Okay. All right, so, no, plus I squared. Yeah, okay, now it works out. Okay, so I got minus 1, and I squared is minus 1, right? So the answer is I get 2. Okay, so when I multiply this thing over here times this over here, I get 2. So I'm going to get a 0 here when I add. Okay, so this better work out, right? Otherwise, it's not an eigen. Okay, so now what you do is you just do everything like you normally would, with Gaussian elimination. You have a free variable, et cetera, et cetera. So I'm going over this slowly just to make sure that working with complex numbers and working with real numbers are basically kind of the same, except with complex numbers, we just have to be a little bit more careful. Okay, so this is free. And so we get -1 minus I minus, so this is x1, minus 2 times x2 is 0. So -1 minus I, x1 minus 2t is 0. Okay. So then I just move everything to the other side. So -1 minus I, x1 is equal to 2t, and x1 is equal to 2 over -1 minus I t. Okay, so this actually brings up a good point. So a lot of times we don't like the complex number to be in the denominator. So to actually get the complex number to be up in the numerator, what do we have to do? Right. So if I take 2 -1 minus I, and I take its conjugate, -1 plus I, -1 plus I. So I multiply top and bottom by the conjugate. Okay. So what do I get? I get -2 plus 2I. Okay. And on the bottom, what do I get? I get 1. So I get 1. The middle terms cancel out. Okay. And then I get minus I squared. I squared is -1. So I get another +1. Okay. I squared is -1. So minus I squared is +1. Okay. All right. So now everything becomes rather nice and clean. Okay. All right. So now we can write x1 in a nicer way. We just have to be patient with it. That's all. Sorry. What?
For that where it's 1 plus 1 on the bottom. So it's all divided by -1 plus I.
Sorry. Are you talking about the denominator?
Yeah.
So I have -1 minus I times -1 plus I. So the first term is,
So when you were simplifying everything, -2 was 2 over 2.
oh yeah. Sorry about this. Thank you. You're right. Thank you. That's exactly right. Sorry about that. Yeah, thank you. Very good. Okay, so it's actually even better. Okay, so now you have to divide. So this is -1. And make sure I don't make mistakes. That looks better. Okay. All right. So when you take the null space of A minus lambda I here, this is the basis for this is going to be equal to -1 plus I and then a 1 here. Okay. It's one dimensional, it's spanned by this vector. Okay, any questions on this? Okay, now I'm going to repeat for, let's see, which one did I get? -1 plus I. Okay, so I think it's this one over here. So so repeat. For lambda equals, okay, so what's the other eigenvalue? It's the conjugate of this thing, right? 2 minus it. Okay. And then the null space here. Okay, so you just do the computation again. And I think it's -1 minus I. And then 1 here. So this should be a 1 also. Okay, so you just do the same thing and you get the null space for the other. Computation is basically the same. All right. So the last topic I'm going to talk about today are rotations and scalings. Okay. And then what we'll do is I'll actually show you a theorem, at the beginning of next class. So rotations and scaling. All right, so this is kind of neat. So you wouldn't expect that this would actually happen. So let's say I take A, and this is going to be equal to A minus B, B, A. Okay, so I take this matrix, and it's kind of innocuous. It's a 2 by 2 matrix. All right. So first of all, let's find the eigenvalues. So if I take PA of lambda, this is determinant of A minus lambda I. So it's A minus lambda minus B, B, A minus lambda. Okay. So you just write this out. This is going to be A minus lambda squared, and then it's going to be plus B squared. So it's like a plus B squared. Okay. All right. I'm okay with this? All right, so let's see if we can work this out. So, so this becomes A squared minus 2A lambda plus lambda squared plus B squared. So this is going to be equal to lambda squared minus 2A lambda plus the quantity A squared plus B squared. All right, so let's see if we can find the roots for this. Okay, so we set this equal to, ooh, what happened here? It's like they want me to move. Okay. So let's find the roots of this thing. All right. So we use the quadratic formula. And what do we get? We get lambda. Okay, so minus B, that's 2A, plus or minus B squared, which is 4A squared, minus 4A is 1 in this equation, and C is A squared plus B squared. Okay, all over 2. Okay, everybody all right with that so far? All right, let's simplify this further. So this is going to be 2A plus or minus. Okay, I have 4A squared minus a 4A squared plus, minus a 4B squared also over 2. So that's 2A plus or minus the square root of minus 4B squared all over 2. Okay. Well, what do we get? Well, the 2 will cancel. So this is A plus or minus B times I. Right, because the square root of 4 is 2, the 2's will cancel. And then you get minus B squared, and that's going to be B times I. Right, everyone all right with that? We skipped a few steps, but does everyone see how that's true? Okay, good. Well, that's pretty neat. So the eigenvalues are just going to be the complex numbers A plus BI. Okay. So these are the eigenvalues. All right. Okay, now I want to set R, so, in the complex plane, this eigenvalue looks like AB out here. So, you should sort of think about polar coordinates. So this is theta. All right, so I'm just kind of rotating this vector theta degrees from the x-axis. And the distance to that point is just a squared plus b squared. Okay, that's just the distance formula. So let me call this the distance, or just the length of lambda. All right. And so now you can write your A as follows. So I can write my A as a diagonal matrix times the following. A over R minus B over R, B over R, A over R. Okay, so when you multiply everything out, you get the original matrix back again, all right? But what is A over R? Well, I can write it in terms of the angle theta up here because I know polar coordinates, right? So if you do this, let me just, okay, so I'll just give you the formula. I'll leave that as an exercise since I'm running out of, no, I'm okay. So this is cosine theta minus sine theta, and this is sine theta cosine theta. Okay, so you can kind of see that A over R is equal to cosine of theta, right? So so x is equal to r cosine. So the x coordinate is equal to r cosine of theta. So you should think of A as being x, right? And this is just polar coordinates, right? And so this is polar coordinates. Remember, x is equal to r cosine theta, y is equal to r sine theta. Okay, so it's just all it is polar coordinates. All right, now, so this matrix here, I'll put it in red. So this is a scaling matrix. So I've written A in terms of just scaling, multiplying by some scalar. And then this matrix rotates. I think we've seen this before. This is a rotation matrix. So it takes a point in the XY plane and it just rotates it theta degrees. Okay, that's what this matrix does. So we've actually expressed our A here, which has complex eigenvalues, in terms of scaling matrix times a rotation matrix. All right. Now, this is going to be important. So let me just preview a little bit why this is interesting. So here's what we're going to prove next time. So we're going to actually state the following theorem. So if A is a 2x2 matrix, with an eigenvalue, which is complex, like completely complex, A minus BI. Okay. So let's say I have a matrix and I know that I don't have real eigenvalues. I have a complex eigenvalue. Okay, so then A is going to be equal to, let's see, P, C, P inverse. So A is going to be similar to matrix where C is going to be equal to the matrix A minus B, BA. All right, so so what this is saying is that whenever you have a matrix with a complex eigenvalue, it's similar to a matrix which is a product of the roots of scaling times a rotation. Okay, so that's what we're saying. Is that, you would think that with matrices with complex eigenvalues, you wouldn't be able to say anything. But it turns out that with an appropriate change of basis, then you can write it as a rotation times scaling. So it's not quite a diagonal matrix. And what I'll do is I'll sort of tell you what the P is and how to get the P. So the P is not going to consist of eigenvalues, but you can still get the P from an eigenvector. So it won't consist of eigenvectors, but you can still get the P from an eigenvector. So I'll mention that next time also. Okay, any questions on this? Okay, so let's stop here. I'll review next time like I did this time, and then we'll probably press on. See you on Friday. Sure.
So we basically just